Hello and welcome to the fourth video on applications of forces for the Year 13 Stats and Mechanics portion of Edexcel A-Level. We're going to extend our ideas and knowledge from dealing with simply static particles to dealing with static objects, for example, such as rods and ladders. So these aren't going to be particles anymore, but actually more sophisticated systems. But they are still going to be static. We're going to look at dynamics later on. To get you warmed up, I've got two questions for you to have a go at. Here they are. So as ever, pause the video, try them yourself, and then when you're ready to see the solutions, press play and I'll guide you through them. Let's have a look now together at warm-up question 1. For warm-up question 1, we're told this is a light, inextensible string connecting two particles P and Q of mass 3 and 7 kilograms respectively. A horizontal force of magnitude F pulls particle Q along a rough horizontal plane. So this is the first big clue. It's rough and horizontal. So we can now just add in P and Q. So if that's P, I'll copy that and add in Q to go alongside it. So there's P and Q on the rough plane. They're connected by a string. So let's add this in like so, and label on what they are. So I'll call this one P, this one Q. So F is pulling Q along. So I'll add in F like this and label it as such. As well, now we've established it's a horizontal plane, we can add in the weights as well. So because P has mass 3 kilograms, its weight will be 3g going down, and in the same way for Q, that'll have a weight of 7g. There'll also be normal reactions from both, so there'll be a normal reaction from the surface on P, and a normal reaction from the surface upon Q. That arrow is not quite straight, so I'll label this reaction subscript P, this one reaction subscript Q. And of course, if it's a string, there'll be tension acting away from each object. So the tension will be acting away from P, and it'll be acting away from Q this way. So because it's a rough surface, we're also told that there's going to be friction involved. So particles P and Q experience a constant frictional force of 8 and 12 newtons respectively. So we've got here that P has a frictional force of 8 newtons, so I'll label this on. Whereas Q has a frictional force which is 12 newtons. So first thing we need to do is to find the tension in the string. A big clue here, though, is that the particles are moving. However, they're moving at constant speed. If they're moving at constant speed, that means the acceleration is 0. Therefore, no net force. So, overall force is 0. In other words, the system is in equilibrium. Now, this is something people often forget. A system can still be in equilibrium if it's moving, so long as there's no acceleration in any direction. So for tension in the string, we can consider either P or Q. So for A, I'm going to suggest that we consider particle P. So for P, we can think of forces going horizontally. So for P or for Q, for some of the forces going horizontal, it'll be in 0, because like we said, the system's in equilibrium. So the forces acting to the right, which are the tension plus, well, nothing else, just the tension. So the tension here must be equal and opposite to this 8 newtons. So the tension must equal 8 newtons. P isn't experiencing any net acceleration, so the forces going to the left, which are 8, must balance with the forces going to the right, which is just T. So the tension must be 8 newtons in this string. Next we have to find the value of f. So for b, what we might want to do for b is consider the whole system. And if we do that, we need to remember, when considering the whole system, the internal forces will cancel out and be equal to 0. In our case, this means the tension. So there's no tension that we need to consider. All we need to consider here is just the net force going to the left and to the right. So the net force acting to the left will be the sum of these frictional forces, 8 plus 12, which is 20. The internal tensions will cancel, and the only force acting to the right, therefore, is just simply F. The system's in equilibrium, so we can now deduce that F must equal 20. We could, if we really wanted, add in the weight and the normal reaction for the system. However, we're only considering forces acting in the horizontal direction, so we don't need to consider that in this particular case. Finally, for part C, we have to explain how the modelling assumptions that the string is light and inextensible have been used. So for that one, we can just simply say if the string is inextensible, the tension experienced by P and Q will be the same. So tension experienced by P and Q will be the same. Another way of saying that, you could say the tension is constant throughout the whole length of the string. Something to just mention, the tension is invariant throughout the whole length of the string. It doesn't change from one piece to the next. Let's have a look now at warm-up question 2. So now we have a dreaded scale pan. You may have encountered one of these from year 12. This time we've got a scale pan of mass 0.5 kilograms is attached to a vertical light inextensible string. The scale pan carries two masses, A and B, of mass 2 kilograms and 3 kilograms respectively, so we may as well add this information on. That's 2 kilograms, that's 3 kilograms. A is on top of B, like you can see. The scale pan is raised vertically using this string with acceleration 0.1 meters per second squared. Find the force exerted on mass A by mass B. So we can also label on, by the way, of course, this acceleration is 0.1 meters per second. So just add this on as well. That's going up. 0.1 meters per second squared. Don't ever feel afraid to do a bigger magnified version of the diagram. This is what I'm going to do for part A. The force exerted on mass A by mass B. So what I want to do here is just sketch out what's happening with A and B. That's B and that's A. So mass A will have a reaction force coming from B on its base. So A will have a reaction force from B acting up, like so. I'll call that just R subscript B, because it's coming from B. And as well as that, of course, A will have a weight. Its own weight is going to be 2g, because its mass is 2 kilograms. So for particle A, if we apply F equals ma in this direction, then the resultant force going up is Rb, which acts up, minus 2g, which is acting downwards. That's the resultant force going up. By Newton's second law, that will equal the mass of A, which is 2 kilograms, multiplied by the acceleration. However, we know the acceleration is 0.1 meters per second squared because, well, because it's said. So Rb minus 2g equals 2 multiplied by 0.1, which is just 0.2. So therefore, the reaction at B will be 2g plus 0.2, which we can work out fairly simply using the calculator. So 2 times 9.8 plus 0.2, that gives us 99 over 5, which as a decimal is 19.8 newtons. Next, we need to find the force exerted on the scale pan by mass B. So similar for part B, I'm going to do the same idea. I'm just going to sketch on here the forces acting from B on the scale pan. So if I sketch a similar system here, like I did before, this is B, and this is the scale pan. In fact, never mind. I'll move this slightly out of the way. So I'm going to draw on the surface of the scale pan here. That's going to be A on top. So think about what's happening to B. Well, B has a weight 3g going down. From B as well, we'll also have a reaction from the scale pan pushing against B. So I'm going to do here a line called RP. This means reaction from the pan, scale pan. I could put R subscript SP, I suppose, or R subscript S. But this is the reaction from the scale pan. And as well, from part A, we found that there's a force exerted on mass A from B of 19.8 newtons. By Newton's second law, that also means that box A will exert that force equal or in the opposite direction onto particle or box B. So there'll be a force going down as well of that 19.8 newtons, which B is pushing up onto A. A reaction has an opposite reaction, as it were. So these are the forces acting on B. Reaction from the scale pan, its own weight, and the normal reaction from A above it. So what we can do here is we can consider forces vertically. So for B, let's do F equals ma going vertically. So going upwards, we've got the reaction from the scale pan. We've got 19.8, the reaction from A, which is the same as B's reaction on A, minus its own weight, so minus 3g. That'll equal its mass multiplied by its acceleration. The acceleration of the whole system is 0.1, so 0.1 multiplied by 3 will give 0.3. So therefore, RP is 0.3 plus 19.8 plus 3g so 0.3 add 19.8 plus 3 multiplied by 9.8, that gives us 49.5 newtons. So we've worked out that the scale pan is applying a force of 49.5 newtons onto B. Therefore, by Newton's second law, the force exerted on the scale pan by mass B will also be 49.5 newtons, because it will be equal and opposite to the force exerted on it. So therefore, by Newton's second law, the force exerted on the scale pan call it the pan by B is 49.5 newtons, which we worked out. For C, find the tension of a string, what we could do is just consider the system as one. So considering this as a whole system, so we've got the scale pan, which is, and everything inside it we can consider here. So we've got the scale pan itself, which has a weight of 0.5 g, because it's got a mass of 0.5. A has a mass of 2, B has a mass of 3, so the entire mass of the system is 5.5, so it'll have a weight of 5.5 g. And the only thing acting up on the entire system is the tension in this string. So if I just label that T. Then we can apply Newton's second law on this as well. By the way, sorry, I mean to say that was Newton's third law from earlier. Newton's second law is F equals ma, so this is Newton's third law. Every force has an equal and opposite force. For the whole system, so the overall force acting up will be the tension minus 5.5 g. That'll equal 5.5 A. Of course, A is 0.1, so we can say T minus 5.5 g equals 5.5 times 0.1, which is just 0.55. So therefore T is 0.55 plus 5.5 g Let's see what this gives us. 0.55 plus 5.5 lots of G, 5.5 lots of 9.8. That gives us 54.45 newtons. And that's the warm-up concluded. So let's now have a look at some questions involving friction and statics. Static rigid bodies. So, to get started, a few ideas and pointers for you. If ever you need to consider rotational forces acting on an object, you can model it as a rigid body. For any rigid body in static equilibrium, the body's stationary, that's the first and most obvious point. The resultant force in any direction is zero. As well as that, the resultant moment will also be zero if you take the moment about any point you choose. Sometimes you need to consider the moments acting on the body and the resulting forces acting on the body separately. So it combines ideas from Chapter 4, moments, and Chapter 5, which was forces and friction. So in some scenarios you need to consider both moments and frictional forces too. Let's put it straight into practice with a worked example. So first of all, we have a uniform rod, AB, of mass 40 kilograms and length 10 meters. It rests with the end A on a rough horizontal ground. So it also rests against a smooth peg C, where AC is 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. So this is quite a lot of information to take in. So it's at 15 degrees to the horizontal, so let's draw in the horizontal first of all. We're also told that A is on the ground. So A, we can write here, A is where it's at the ground, but it's lifting up at an angle of 15 degrees, like so. We're told that the full length of it from A to B is 10 meters. So we can label this on so we don't lose track of the initial conditions we were given. From there to there is 10 meters. And it's inclined at 15 degrees because we were told that too, so that can be added in. So what else can we do here? it says here it's resting against a smooth peg, C. So a peg just means it's like a rod which is going into and out of the page. So the peg is like going into the page and will be in a parallel flat line. So the peg won't be tilting up or down. It's like, imagine it resting against a straight pencil or something. So something like a pencil or a rod is supporting this beam. So a peg can be modelled as circular. So I'm going to call this peg C, and from A to C is 8 meters. So that could be peg C, and that's 8 meters up. In fact, I'll just label this from there to there as 2 meters, which essentially is the same thing. If that's 2, from A to C is 8. It's mentioning about the magnitude of the reaction at C. So obviously, there will be a normal reaction from C against this rod, pushing it up like so. So I'll label that R. Any other things we need to consider? Well, actually, yes, there is. So never stop until you've considered everything. We're told this rod is in limiting equilibrium and the ground is rough. So let's consider, if this was smooth, which way would the rod want to fall? Well, it wouldn't slide up, B wouldn't get higher. That would just be weird. If anything, A would slide down this way. It'd slide down to the left. Friction will always oppose any possible motion like that, and so the friction must be working to the right to prevent it from slipping to the left at A. So we can add in this line here for the friction, but we're also told that it's in limiting equilibrium. So what this means is the friction will be F max, which will be mu multiplied by the reaction. Now, problematic this is because we've already got a reaction force here at C. This friction at A will be based off the reaction from A. The reaction from C has got nothing to do with the friction down here. So what I'm suggesting we do is we give this reaction force a subscript of C. So that means reaction at C, to distinguish it from the reaction from A, which I'm saying we could label in as R subscript A. So this friction is mu RA, because it's F max. Finally, last but not least, we need to consider if this rod has a weight or not, and it absolutely does. It's a uniform rod, which means its weight can be considered halfway along its length, and it's got a mass of 40 kilograms. So therefore, we need to add in its centre of mass here, and the magnitude of the weight will be 40g. So that's now a fully labelled force diagram. We've not resolved any forces yet. Sometimes you don't need to. Let's just see what the question's asking. First of all, it wants us to find the reaction at C. So the reaction at C, there's lots of unknown forces here. There's 2 unknown forces at A alone. If you can remember from chapter 4, moments are best taken at the point where you've got multiple forces going through it. If you take moments about a force with different forces going through it, those forces have no distance from their line of action to that point, therefore they have no moment themselves. So we can take moments about A, and if we did that, RA and the friction becomes something we can not need to consider. So for part A, let's think about taking moments about A. Because it's in equilibrium, we know that the clockwise moments must equal the anti-clockwise moments. So relative to A, going clockwise, we have the weight. So the weight is 40g. For moment due to the weight is the force, in this case for weight, multiplied by the distance of the line of action from that force to point A. So what we need to do here is just consider what this distance is here, like so, from that end to that end. What we need to do here is actually use some trig. From A to C is 10, the centre of mass will act at the midpoint, so we know from A to the centre will be 5. Essentially we want to work out the adjacent side of this triangle here. So from A to that point there, that's actually going to be 5 cosine 15. So 40g multiplied by 5 cosine 15. That's a moment due to the weight which is going clockwise this way. That must equal the moments going anti-clockwise, which will only come from the reaction at C. So that's going to be the reaction at C multiplied by the perpendicular distance of the line of action of C from A. Well, from C to A it's already at right angles because it's a normal reaction, and we're told for A to C is 8 meters. So if we just rearrange this now, we can see that RC is 40g times 5 cosine 15 divided by 8. Let's see what we get. So 40 multiplied by 9.8 multiplied by 5 cosine 15 divided by 8. That gives us approximately 237 newtons to 3 significant figures. Now for part B, we need to consider the coefficient of friction which is in play. So to work out the coefficient of friction, there's a few different approaches we could use. Ultimately, we need to realise the coefficient of friction is going to be based off the reaction at A. So we could do with finding this reaction at A. So let's consider forces going up and down. Now because the system's in equilibrium, the forces going up and down will sum to 0. So the forces going up, we've got RA. We'll also have a certain component of RC as well, but RC isn't going vertically up, it's going sort of diagonally up. So what I'm suggesting we do here is try to work out this component which is going vertically for C. So what's this vertical component of C? Well, first off, we know that the inclination is 15 degrees. So if we just consider some GCSE Z angle work, then we know this bit's 15 degrees. However, this rod and the reaction are perpendicular, so the whole angle's 90. This bit's 15 based on alternate angles. And so the angle that this makes with horizontal, this force, is going to be 75 degrees. So the vertical component of reaction at C, the component going vertically up, which is the direction we want to consider, is going to be the reaction at C multiplied by sine of 75. So RA plus RC sine 75, this bit here, they're the only forces or components of forces acting vertically up, they must be equal and opposite to the forces or components of forces acting vertically down, which in this case we can see is 40G, the weight of the rod itself. So therefore, the reaction at A is going to be 40G minus RC sine 75. Now we've got the reaction at C stored in its exact form on this calculator, so let's leave that as it is. So that's our answer which has been stored. So reaction A is 40G, 40 multiplied by 9.8, then minus that answer we've got stored multiplied by sine of 75. And that gives us approximately 163.411 and so on. So 163.411 blah 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 newtons. Now we can consider forces going left and right. So if I just section this off here to give myself some more space, can't seem to do a straight line today, it's just very upsetting. But never mind me complaining. Right, so now we can consider forces horizontally. So the sum of forces going in a horizontal direction will equal 0. So the only forces going to the left we can see, without having to resolve, going to the left, the only thing we've got going to the left would be this component of the reaction at C. So again, we can consider adding this in. So that component of C which is acting that way is going to be the magnitude of the force, then cosine 75. So therefore, the forces acting to the left, RC cos 75, must be equal and opposite to mu RA. But mu RA is mu times 163, whatever it was. So therefore, if we just divide both sides of this by 163 now, we can work out what mu is. So mu is going to be RC cosine 75 divided by 163. And that'll tell us what we've got, because we worked out RA already, which is this 163 business. So finally that's stored in the calculator. The reaction at C was 237 newtons. Then I'm going to multiply that by cos 75, then divide that by my previously stored answer, like so. And I get here 0.375 to three significant figures. So mu is approximately 0.375. This second question, as you can see, it's a ladder. So it's a ladder AB, mass M and length 3A. It's got one end A resting on rough horizontal ground. So that first sentence we can already begin to add in a fair bit of information. So what we can do here is add in the weight of a ladder. Okay, so what we need to do is consider where the weight of the ladder will act from. So you can probably guess, and if not, you probably should be guessing, and if not, you should be told. The ladder is modelled as a uniform rod. So based off that fact, we need to add on its weight, because it's uniform, the weight will be acting from halfway along its length. Its length's 3a, so therefore the weight of the ladder will be acting at a point 1.5a away from A and B. So it's got a mass m, so I'm going to label on here just mg going down. More than that, we were told as well that it's on rough horizontal ground. So if the ground was slippery, had no friction, the ladder would slide to the left, it'd go down. So the friction would act to stop that, so friction is going to be opposite direction. The friction therefore would be acting in this direction to the right hand side. So that's friction, F. There'll also be a reaction force acting from A, a normal reaction force going up like so. I'll label that RA. Could also label it reaction of the ground if I wanted, but I'll call it the reaction from A. And it says here, the other end B rests against a smooth vertical wall. So this wall has no friction, but it will again have a reaction. So it'll be a normal reaction acting perpendicular to the surface of the wall. So just as this was a right angle here, this will be a right angle at B, and I can call that R subscript B. So what else are we told? So at C, there's a load of mass 2m fixed at the ladder at C, so I need to add on that weight as well. If the load's 2m, the weight will be 2 mg. So AC is A, that's been labelled. The ladder is modelled as uniform rod, which we've used so that we can actually put on here the weight acting from 1.5A along. I can add that on now actually, if wanted to, so that's 1.5A. So it's in limiting equilibrium. Because it's in limiting equilibrium, that means the friction will be F max. It'll be a maximum friction, which will therefore be the coefficient of friction mu multiplied by the reaction at A. So we know that because we're told it's in limiting equilibrium. So F is F max. So for part A, we need to find the coefficient of friction between the ladder and the ground. The maximum friction relates to the reaction from the ground, so we need to work out RA. So RA acts vertically upwards. For systems in equilibrium, so let's consider forces going up and down. So for part A, because it's in equilibrium, we can say that the forces acting in the vertical direction are balanced and are therefore sum to 0. So forces going up, well, we only have RA going up, so RA, the reaction from A, equals the forces acting down. So we've got mg acting down, plus 2mg also acting down, mg plus 2mg, that gives us 3mg, obviously. We can now think about forces going in the horizontal direction. So let's consider forces horizontally. Because it's in equilibrium, they'll also sum to 0. So using that idea, with any forces acting to the right are F max, which is mu RA. So mu RA. We now know, though, this is mu times 3mg. Because we calculated that RA was 3mg here. So that's the force going to the right. The only force going to the left is just the reaction from the wall, the reaction from B. So what I could choose to do here is I could say that for reaction at B, it is actually mu times 3mg. It's 3 mu mg, which is the same as the maximum friction down here. It's one and the same thing. It has to be that way because it's equilibrium. This force to the right has to be equal and opposite with this force to the left. So, reaction at B. So, at A, it's quite messy down there. There's lots of, well, unknowns. Well, we don't know mu, and reaction of A as well is still there. So, we can choose to go a couple of different ways now. What I'd suggest to do is we could take moments about A. Then it just takes away all this mess here. So consider moments about A. Because the system's in equilibrium, the clockwise moments will equal the anti-clockwise moments. So clockwise equals anti-clockwise. So relative to A, going clockwise, we have these two weights. The weight of the load 2m and the weight of this m. So 2mg and g. So what we need to do here is work out the moments due to these forces. So we've got 2mg. So that's a force. The moment is a force multiplied by the perpendicular distance of the line of action from that force to the pivot we're taking the moment about. So we don't know it yet. What we do need to find out though is this distance here. So from 2mg to A, we need this distance in blue. So we need to consider this right angled triangle. Hypotenuse A, blue side there, that angle's 60. So that adjacent side in blue would actually be A multiplied by cos 60. Then we've got the mg force, so the force is mg, multiply that by the perpendicular distance of the line of action of this force from A. Well, in the same way as what we did for the 2mg force, it'll be this distance from here to there, which I'm doing in this purple line. So this is like a bigger triangle to this point here. Now from A to the midpoint, that's 1.5A. So now I'm talking about this hypotenuse. It isn't just A, but it goes up to the midpoint. From there to here is 1.5A. So this purple line will be 1.5A times cos 60. And those are the only clockwise moments acting relative to A. They must therefore equal and be opposite to the anti-clockwise acting relative to A, which is just this RB force up here. So the magnitude of the force at B, the reaction from B, is 3 mu mg. And the perpendicular distance from that line of action to A is just simply this distance here. So it's all the way from the top to the bottom, because that's perpendicular. So consider this whole triangle. It's basically the height where it's rested against the wall. The hypotenuse of this side is basically the length of the whole ladder, which is 3A. The opposite side, we do 3A sine of the angle. So this green length here is 3A sine 60. That looks pretty unreasonable, looks an absolute mess. But just think about what we could cancel from each side for a moment. What's common in each term? Well, in each term, there's an M, there's a G, and there's an A. So we can cancel M, G, and A from each term in turn. Now I'm just going to suggest we just write this a bit neater. So we're not actually going to do anything apart from just cancel the m, g and the a. So 2 cosine 60 plus 1.5 cosine 60. We've got 3 times 3, which is 9, mu, obviously, sine 60. So therefore we can now divide both sides by 9 sine 60 to isolate mu. So mu will be 2 cos 60 plus 1.5 cos 60, 2 lots of cos 60 plus 1.5 lots of cos 60. You could, if you wanted, if you feel confident, say it's 3.5 lots of cos 60. If you don't, just leave it as it is in long form, let the calculator do the hard work for you. But here I'm just simplifying. 2 plus 1.5, 3.5 lots of the same thing. Divide by 9 and divide by sine 60. So 3.5 cosine 60 divide by 9 sine 60. I get 7 root 3 over 54. Let's get this into a more normal looking number. Press SROD to 3 sig figs. I have 0.225. Let's now have a look at another example in a moment. We've not done B though. I was almost tempted to move on without thinking about B. Whoops, a daisy, that would be bad. State how we use the assumption that the ladder is uniform in the calculations. Well, that's quite simple as long as you don't lose your head in the exam. We used the assumption that it was uniform to deduce that the centre of mass can be modelled at the halfway point. So we just need to put into words that idea that we've used. So for B, we used that the ladder was uniform to model, I apologise for my awful handwriting, the centre of mass of the ladder as acting at its midpoint, or words to that effect. That will score you the mark. Finally, let's have a look at a past exam paper example. Again, keeping with the topic of ladders here. So this time we've got a ladder AB, mass M and length 2A. Has one end A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 0.6. The other end B of the ladder rests against a smooth vertical wall. So let's start to draw this in. So if I just draw first of all the ground, the wall, and the ladder. So it says one end is at A on the rough ground, so that's A. B is therefore against the wall. We're told this time that the coefficient of friction between the ladder and the ground is 0.6. So we'll come to that in a moment. There is going to be a normal reaction acting at A, so I'll call this R subscript A. And like with example 2, you'll know as well that there will be a normal reaction from the wall in this direction, which I'll call R subscript B. So this wall's smooth, so no friction, so that's good to know. However, a builder of mass 10m stands at the top of the ladder. So let's add in this builder. So builder, mass 10m, is standing at the top of the ladder. So we can model this builder being right at the top. He or she has a mass of 10m, so I'm going to do a line representing the weight of this builder to have a weight of 10 mg. acting downwards. As well as this, we've not actually added on all the information from the first paragraph yet, so that was a bit naughty of me. It's a uniform ladder, so it's going to have weight acting at its middle. It's got a length of 2a, so its mass we can consider being acting from the centre, and because it's got a mass of m, the weight associated with that will be mg. And of course, this is length A, like so. So next it's saying, to prevent the ladder from slipping, the builder's friend pushes the bottom of the ladder horizontally towards the wall. So presumably just this bloke or something, or woman, is holding the ladder here with their foot. Sorry, I'm trying to avoid any gender bias. The builders could be men or women. It is bad that I'm saying this in 2021. Apologies, honestly. Anyway, yes, so the builder, they're holding it there with their foot so it doesn't slip, so they're trying to protect their friend. Very nice. And the force is acting in a direction perpendicular to the wall. So I need to draw in this force P. So this force P is acting this way like so. It acts in a direction perpendicular to the wall, so yeah, that's going to hit the wall at 90 degrees. The next thing we're told is that the ladder is in equilibrium and it's making an angle of alpha with a horizontal, where tan alpha is 3/2. So if I call this angle here alpha, it says tan alpha is 3/2. So I'm just going to cling to this point for just a moment. So tan alpha is 3/2. So if we imagine now a right-angled triangle, get it a bit better, there we go. So if we've got alpha, call it alpha there. Tan is always opposite divided by adjacent. So if the tan ratio is 3/2, that means that the opposite and adjacent are in the ratio of 3:2. We can now use some simple Pythagoras to work out, relative to this side, the opposite and the adjacent, what the hypotenuse would be. If hypotenuse squared is 3 squared plus 2 squared, which is 13. Therefore, this hypotenuse would be the square root of 13. We can now use the idea of what sine alpha and cos alpha would be. If you don't like this way, by the way, you could just do tan minus 1 of 3/2 to get what alpha is in a horrible decimal form. That's fine. I was trying to get you to think of these angles when they're given in this form in a different way. Anyway, so sine is opposite over hypotenuse. So sine alpha would be 3/√13. And cos alpha, which is adjacent over hypotenuse, that'll be 2/√13. Like so. So we've labelled on, I think, enough now. First of all, part A, it says show that the reaction of the wall on the ladder is 7 mg. So what we can do here first is try to think how we can find this reaction. The trouble is there's also going to be friction as well. So the friction would tend to stop the ladder from slipping. The fact that this person is pushing this way implies he's trying to give the friction a helping hand, because the friction on its own might not be enough to hold it in place. So I'm going to say the friction is also acting this way. I'll call this F. So now show the reaction on the wall. We've got lots of different forces acting at A. We've got this force that the builder's friend's pushing against, we've got the friction, we've got the reaction from A. So if we were taking moments, a really good place to take moments about would be A, to eliminate having to think about all these forces. So let's do that. It's almost begging us to take moments from A because A is looking a mess. So for A, let's do moments from A, moments about A. So clockwise will equal anti-clockwise. So the moments going clockwise for A are going to be these weights, the mg and the 10 mg. So this mg force for weight will have a distance away from A from here to here. And so what we consider here is this triangle, which I'm just tracing over here, with hypotenuse A. If its hypotenuse is A and the angle's alpha, this distance here will be A cosine alpha. So A cos alpha. And the 10 mg force of the person standing at the top of the ladder has magnitude 10 mg. So that moment will be the force multiplied by the perpendicular distance of the line of action of that force from A. So we're talking this entire bottom distance of the triangle made with the ladder, the ground and the wall. This has a hypotenuse of 2A, the whole length of the ladder, angle alpha, so this adjacent will be 2A cos alpha. That will equal the anti-clockwise moments, which is just the reaction from the wall at B, so that's going to be RB multiplied by the distance of that force from A, the perpendicular distance. So that's from here all the way down to there. So that's the opposite side of this big triangle. So the bottom adjacent was 2A cos alpha. This distance here is going to be 2A sin alpha. But now we can use what we worked out earlier in this little triangle here. So what we did is we actually thought about what sin alpha would be in terms of tan alpha. Sin alpha we can replace with root 3 over 13, and in the same way we can replace cos alpha with 2 over root 13. So if we do that next, so here we're going to have 10, so we can have mg times A times cos alpha, so that's going to be 2 AMG over root 13. Over here we've got 10 mg multiplied by another 2 A, so that's going to be 20 AMG, but this time that multiplied by cos alpha is going to be multiplied by 2 over root 13. And then over here we've got reaction from B multiplied by 2A sin alpha. So that's 2A times 3 over root 13. Now this here looks horrible. What I'd suggest you might want to do to make it just look more humane, just multiply all sides by root 13. Just to get rid of that horrible surd. Now what we'd have is 2 AMG. 20 times 2, that's 40 AMG. And over here we're going to have 6A RB. Therefore, RB, for reaction from the wall, 2 AMG plus 40 AMG There's going to be 42 lots of AMG. Divide by 6A. So the A's will cancel. So 42 divided by 6 will just leave us with 7 mg as required. So we wanted to prove that, and we have done here. Finally, for part B, we have to find, in terms of m and g, the range of values of p for which the ladder remains in equilibrium. So this is a bit harder to get our heads around. What we need to do here is work out what the maximum friction would be. And to do that, we need to work out what the reaction from A would be. So considering forces going up and down, the reaction from A, for any force going up, must be equal and opposite to the forces acting downwards, which is just mg plus 10 mg which gives us 11 mg. Therefore, the maximum friction, which is mu times by r, we were told in this question what the coefficient of friction was. If I just scroll up to show you, the coefficient of friction was 0.6. So Fmax is 0.6 multiplied by the normal reaction force, Ra, which is 11 mg, which will be 6.6 mg. So the friction can resist with magnitude 6.6 mg. So if that person took their foot away, there'd be 7 mg pushing against it. The 6.6 mg wouldn't be enough. And so what would be needed is that person would need to provide another 0.4 mg to get the total of the forces to the right up to the 7 mg to counteract that reaction from B. And so P would need to be at least 0.4 mg, because 0.4 mg plus 6.6 mg would just about cancel out this 7 mg. That would be in a limit in equilibrium. Now, if P increased any further, for example, if P were, say, mg, it would be a force of 7.6 mg going this way, so there would be an overall force without friction acting to the right, so the friction there would actually act in the opposite way. So the friction would switch sides. So if this person was pushing really hard to the extent that the ladder was going to push towards the wall from the bottom, the friction would be moving over here. That would still be 7. The maximum friction that could be acting to the left would be 6.6. 7 plus 6.6 gives us 13.6. If P was any greater than 13.6, P would prevail over the friction and the reaction from the wall. So we need to put 13.6 mg. Another way of thinking about this is as follows. So I'm putting this in brackets. So P needs to be the reaction in between the reaction minus Fmax and the reaction plus Fmax. And that's where those numbers have come from, in case you're wondering about my explanation being a bit iffy, or in case you didn't follow it the first time. Over to you now. I want you to try these questions on your own. Page 144 to 146, exercise 7D in the Stats and Mechanics book. Questions 4 through to question 11 would be a suggestion which I'd follow. Okay, thanks so much for listening. Do please subscribe, and I'll see you all in lesson or on the comments section. So thank you, and bye for now.